Okay. I don't know if you can hear me. Hang on, hang on. Good morning. Good morning, Melanie. Thank you. I needed that actually. Good morning, Lila. Thank you. I needed that. Good morning, Michelle. Good morning, Luke. Thank you. I needed that. I'm gonna not say that every time, but I did. Good morning, Jaden. I'm going out of order. Good morning, Juan. I appreciate it. Okay, Melanie. Yes. Josh. Good morning. I missed that. Sorry. I see you now. My bad. Nadine, good morning. Jalila, good morning. Luke, good morning. Mohammed, good morning. Jaden, good morning. Juan, good morning. Michelle, good morning. Alicia, good morning. Shrutika, good morning. All right. Thank you all for being here. Give me a second. I totally get why there's a little less video than usual. There is for me too. I get it. Hold on. Running a little ragged too. Give me a second. But you can hear me, right? Wait, can you hear me? Uh, yes, thank you, Jaden. And that's points right there. All right. Give me a second or 17. Hold on. I know. Oh, and that's I just saw, but thank you. I didn't see. I saw something. Hold on. Okay. I'm saying 1 second, but I'm lying. Bear with me. I'm sorry. This is all bad form. I'm okay. Well, I'm lying again. Okay. Okay. There's that. Um, I'm looking in the chat. Jaden, yes, thank you. Okay. We, all right, give me 1 more second, and I will change the view and all that's good stuff. Um, you are this cloud. Okay. I'm looking at, okay. Okay. So look, ay, 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 ay. It is crazy times. And I mean, so to speak, in the language of certain traditions that celebrate certain things around this time of year, the plagues have come early this year. I'm sure you've had a very rough, I gather you've had an intense weekend, um, to some extent in my hand, maybe at every extent to my hand. I don't want to dwell on that, right? I want to congratulate you. I mean, I see that just about any exam that isn't in yet is because of an arrangement that was made or a communication or something. I get and just about every exam is in. So congratulations, and you're here, which I know is not easy. Hopefully, maybe it was slightly easier to be here than to be on campus. I don't know. Maybe it's harder. I definitely get why you're not showing video. I'm sure you're half. I get it. I also am dealing with stuff, as you know, in health and household and child who's upstairs and all that kind of stuff. So we're all doing our best, but I do congratulate you on being over a certain hump. We'll find out soon how you did and all that, but I think you did. The mere fact that you got over that hump and that it's in and that we're here together is an amazing accomplishment. I'm not being sarcastic. Now I'm not going to deal with that at all right now. There's nothing to be done. Like we're moving on now. We're here to stay on top of the curriculum, which you guys have really done this semester. Um, we're here to move on with the curriculum. So the good. So and I'm gonna, well, here we go. Right. So the good news and the bad news, well, the news is that we're about to shift gears entirely. Like any thoughts that you have about the material of the exam or your work at the exam or your stress at the exam, like you could wipe them clean for a moment, for an hour. Um, every We're going to shift gears entirely on the topic, and um, I need to explain things to you about the new topic, but I recognize that our tanks are not fully full. So if you just take notes and you take this PDF and all that stuff, it shouldn't be that bad. I'm gonna To be even more concrete, I'm gonna tell you now that my main goal today. Wait, you're still with me, right? Yeah, okay. My main goal today, once I switch the view of the screen and start taking notes stuff, the notes that I'm going to give you, the main goal is to make you feel prepared or equip you for the lab that you're going to do. The lab that you're going to do today, right? And the lab, let me say, the lab is a board meeting on an entirely new, well, yes, essentially a new topic. And I had a long, phone meeting yesterday with uh, Professor Brunson. The board meeting. I don't even remember if you've done maybe your first board meeting this semester. I can't remember, but it is you. It would. I hate saying this, but it should be less stressful and less complicated and less brain requiring than sometimes is the case in this class. I mean, in fact, I'm going to say right now, and I'm going to stop introducing and just get to it, but I'm going to say that the main bulk of what you're doing in the board meeting today with Professor Brunson, the main thing is like plug in exercises to practice and see a new equation. I mean, it's a new equation I'm going to start giving you now, but it's not a trick. Is Mostly what you're doing in the lab is plugging in. I mean, some of you will have different tricks for plugging in than others, and that's part of what we want to see. And some of you might, and the numbers are clunky and stuff like that. But don't overthink it. We are we've designed, or we're intentionally trying to get you into this new topic in a way that takes into account the fact that your brains are fried, and that conditions are weird. Okay, honestly, I'm looking. Okay. Okay. So, all right, and someone just answered. Okay. So I'm going to start teaching the concept right now, but specific, and I might even screen share the sheet that you're going to be using in lab, or in fact, I will. But so if you can tune in to some extent, and just know the main goal is so that you're not clueless when you walk into the board meeting today. That's the idea. Can I just get any kind of show of hands that you're still with me, sort of, that you get what's about to happen? Thank you, Nadine. I appreciate it. Okay, and thank you, Jaden, and thank you, Shrutika. Okay, awesome. And again, I'm impressed with all of you. I'm rooting for all of you, and I'm sympathetic to all of you, like for reals. Okay, so I'm going to start on the. Okay, okay. So the topic here, the ultimate topic here is the electrostatic force, electrostatic charge, electrostatic field. I mean, that's ultimately the topic that we're getting into, that we're introducing today. Electrostatics. Okay. I mean, that's the point, and that's the point of the board meeting. the way that we're going to get there is from me sort of reminding you or reviewing with you, or for some of you, freshly stating the universal gravitational force, because the claim I want to make to you today and the claim I want you to see in the board meeting of the lab is that the concept and the math of the universal electrostatic force is remarkably similar to the concept and the math of the universal gravitational force. Okay, that's the point. Switch the view. Okay. Okay. Well, sorry. That's true, but say it a different way. Okay. First here, something that in principle, I think we said at the end of last semester, for those of you who had me, mm, but I'm saying it again freshly now. Here's a concept from mechanics, from Newton. If you have any two point masses in the universe, like a number of kilograms that takes up no space, essentially no space over here, and a different number of kilograms, like squeezed into a tiny infinitesimal volume over here. So, like M1 and M2, and they're arbitrary masses. So, most likely, they're not the same number of kilograms. So, whichever one is bigger, we call capital M1, and whichever one is smaller, we call lowercase m2. If those, given those 2 point masses, and given that they're separated by a displacement vector called r, right? So r is a vector that has magnitude and direction. So it's some amount r times some unit vector r hat, right? Going back to like some of our vector stuff from homework 2. If r is the displacement that points from capital M1 to lowercase m2, if you have that situation, which of course we do all the time in the universe, then sorry, I mean that's true, but just moving it over. Okay. What I'm saying in English here, again, well, what I'm saying in English is if you have these 2 point masses, dots of mass of different amounts of kilograms, different magnitudes, right? You have these two dots of masses anywhere in the universe, and they're separated by a displacement r, for which r means the amount of space between the amount of distance between the two masses, and r has a direction, specifically the direction points from one of the masses to the other mass. Specifically, by convention, it points from the mass that we call M1 and is generally the bigger one to the mass that we call M2 and is generally the smaller one. If that is the case, if that's the situation, what Newton says, what we essentially still believe to this day, is that M1 will automatically exert a force onto M2. It will automatically interact with M2. Like it'll pull or push M2. Specifically, in fact, it will pull M2. Hold on, someone's here. Okay. And it'll pull M2 in the manner of a force vector. In fact, let me, I'm going to write that and then I'll keep explaining this. Okay. What we're saying is, conceptually, what we're saying is you have a bit of mass over here, you have a bit of mass over there. This bit of mass will automatically, always pull on the bit of mass over there. It'll exert a force vector. It'll pull with some amount of newtons in some direction automatically all the time. It'll make a force vector, and that force vector will do what all force vectors always do according to mechanics. It'll be a force vector that gets plugged into the left side of F net equals ma, and it'll contribute to the a, the acceleration of the other mass, of mass 2. Okay, so automatically, if you have a bit of mass over here and you have a bit of mass over there, automatically the first bit of mass will exert a force vector onto the second mass. And because it's a vector, it'll have magnitude and direction. The magnitude and direction will be expressed by, calculated by, predicted by this equation. Now, what does this equation say? Sorry. Okay. What does this equation say? Well, first of all, as far as well, let's look at the magnitude first. And that's, by the way, what you'll be focusing on today in the board meeting of the lab. You'll be focusing all on magnitude. I'm going to say some stuff today in lecture about direction because you need to know it ultimately for the class, but you don't have to get too bogged down in it for the board meeting today. All right. So what's in the parentheses says everything you need to know about magnitude. What's in the parentheses says take the mass, the number of kilograms of mass 1, multiply it by the number of kilograms in mass 2, divide by the square of the distance between them, right? Remember, R vector, R with an arrow over it, is a displacement. It consists of a distance magnitude and a unit vector direction. R, when it's written with nothing above it, means the raw distance, the raw magnitude. So you take the mass of one, you multiply by the mass of the other, you divide by the square of the distance between them. You take that entire, so you'll have kilograms times kilograms over meters times meters, right? You'll have kilograms squared over meters squared. Then you take that entire package of numbers and you multiply by this number capital G, this given, memorized, always the same natural constant number called the universal gravitational constant, capital G. You multiply the whole package by the capital G, you see that capital G is a very, very tiny number, 6.67 times 10 to the negative 11th, right? You multiply by that tiny number and you see that G has units. They look like crazy units, but in fact, they're not crazy units. They're units that are deliberately designed to ensure the whole purpose of capital G, which is to cancel out the meters and the kilograms and leave us all entirely with an amount of newtons, hence the magnitude of a force. In other words, you take the mass of one, you multiply by the mass of the other, you divide by the square of the distance between the two, so you'll have some big number in kilograms squared divided by meters squared, and then you multiply by 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. So the meters squared cancel out, the kilograms squared cancel out, and you're left with some number of newtons that is probably a tiny, tiny number. If you used regular old kilograms like sitting around on Earth and regular old meters, because you multiply them all by this tiny number, 6.67 times 10 to the negative 11th. So you end up getting a magnitude that is very small. And then what do you do with that magnitude? You then multiply it by r hat, and which makes it into a vector. Now it makes it into a vector whose size is that size that you just calculated, and whose direction points from M1 to M2. I'm going to write this down in a second, but you get a vector, a force vector that has a certain size of newtons and points in a direction from M1 to M2. But then there's a negative sign before the whole thing in the equation. What does that negative sign tell you to do? It tells you to flip the vector that you just calculated so that the vector points back at M1. Why? Because that, in the end of the day, I'm gonna draw this now out for you and show you it in a slightly different way. But why? What's the deal with the negative sign? What's the deal with that r hat? If you're following what I'm saying so far, once you take a force vector that was pointing from mass 1 to M2, and then you flip it so it's pointing back at M1, what you're saying now is that the force exerted by M1 onto M2 pulls M2 toward M1. It's attraction. The negative sign means the negative times r hat at the end of the day means attraction, which is what gravity always is. I mean, hence gravity always has that negative sign. I'm going to show you this a slightly different way. We're going to do I'm going to say the same thing, but in the reverse order and with concrete numbers right now. Hold on a second. But wait, are you well, yeah, okay. Hold on. Okay. To remind you of this whole unit vector business and stuff. And again, right now, I'm trying to be very precise about direction and the vector aspect. Just so you, and I want you to write this down. I want you to know this. You need this for later, but this piece, don't stress it for today's lab. Or yeah. But this is the idea. R is the displacement that points from M1 to M2. It has a length of 5 meters and has a direction that points from M1 to M2. So the way we think about that is like, first you think of this unit vector, you think of a little arrow that has by definition length 1, but is there to tell us something about direction. It points from M1 to M2 because we're going to calculate the force that M1 exerts on M2. Okay, so we think of that unit vector r hat that points from M1 to M2, and then we scale up or down. We scale our r hat by a factor of 6.67 times 10 to the negative 11th times 25 times, I forgot, what do we say, times 2 all over 5 squared, which is 25. Do you see, right? I'm literally plugging in. So I'm saying the way the equation is asking. So in other words, when I first introduced the equation 10 minutes ago, I said the piece in parentheses is magnitude and the unit vector is direction. That's true. Now I'm saying the real way to think about physics is sort of not to read it left to right, but read it right to left. To think of the direction first. R hat is just telling you direction. It doesn't change the numbers at all. It's just a little arrow indicator that points from M1 to M2. R hat is telling you something about the direction of displacement. So you take that little arrow that has a size 1 and points from M1 to M2, and then you stretch or shrink that arrow by all the stuff in the parentheses, G times M1 times M2 over R squared, right? In other words, in this case, so G is always 6.67 times 10 to the 11th. I'll put the units in actually. Newtons meters squared divided by kilograms squared times uh yeah times 25 kilograms times 2 kilograms all over 5 meters squared, right? So the kilograms will cancel out, the meters squared will cancel out, right? And in fact, even in this case, the 5 squared will cancel out with the 25. So you'll get the, so here, the force that mass 1 is exerting on mass 2 will be about, I mean, the only thing that'll be left in all that whole multiplication will be that the 2, and so you'll get about 1.33 times 10 to the negative 10th newtons but all pointing in what direction? All pointing in the r hat direction, but then there's a negative sign before it. So what does the negative sign tell you to do? So we have an arrow. What I'm trying to say in the end is we make this little arrow that points to M2. We scale it by a certain amount. So we get this number, 1.33 times 10 to the negative 10th, which is a very small number. And then the arrow, and then we flip the arrow so it points back to M1. So at the end of the day, okay, I'm going to pause again. I'm saying automatically, if we have M1 and M2 sitting there, M1 will automatically exert a force onto M2. The, the magnitude of that force is given by plugging straight into this equation. M1 times M2 divided by R squared times this universal constant G. It literally is a plug-in to get the magnitude. To get the direction, you think about how unit vectors work, and at the end of the day, so you draw a unit vector from M1 to M2, but then the negative sign tells you to rotate that vector 180 degrees. So at the end of the day, automatically M1 will exert a force onto M2 that points toward M1, meaning that automatically at the end of the day, M1 will exert a gravitational interaction with M2 that is in fact attraction, that is in fact a pull as opposed to a push, like always. The negative sign is always there in the equation. The negative sign always means attraction by this logic. The magnitude is something that I want you to get used to. Calculating the magnitude is something I want you to get used to, and you're going to see again in the board meeting today. The direction I want you to hold on to in the back of your brain for like later this week, or later this week and next week, etc. But you won't need to worry about it in the board meeting. last point about the direction. So this force vector that you calculate becomes a force that obeys Newton's laws, specifically Newton's second law and Newton's third law, which means it obeys Newton's third law. And also, multiplication is commutative. So therefore, if all of this calculation shows you what M1 would do to M2, therefore, by Newton's third law, there is necessarily a force that M2 would exert on M1 that would be literally the same magnitude but opposite direction as the force that M1 would exert on M2. Like everything I just said, you could look at from the point of view of M2 and see what it's doing to M1. It'll be the same computation, the same magnitude, but the opposite direction because of Newton's third law. And also because if you just look at the math, like the multiplication is commutative. So in the end of the day, what's the difference between M1 and M2? Nothing except whichever one we're focusing on at any given moment. So, I mean, generally M1 is the bigger one, but that's generally by habit. That's not really, it's not strictly necessary. The real issue is whatever we're calling M1, we're viewing as the thing that's creating the force. So ultimately, what we would call M1 is the source mass. M1 is pulling on M2. And then when we want to talk about what M2 is doing to M1, we would switch the perspective in our mind. So M1 is known as the source mass. M2 could be known as the receiver mass or something like that, but it is what it's ultimately known as, and this is again what you'll see in the lab today. Ultimately, M2 would be known as the test mass. It's because it's like it's there to test the effect of M1 at a certain distance on it. Okay, now that is how gravity works. Let me pause for a second. Again, as usual, in a way, I'm over talking it. In a way, I'm making it slightly more. It is just a plug-in equation, really. I'm just partly using it as an excuse to remind you of how unit vectors work, and like all the aspect of direction is to show you that if you properly put the unit vector in there, you can see how the negative sign being multiplied by the unit vector ensures that this whole thing is attraction rather than repulsion. No, I always do that. Sorry, the law of universal gravitation. There's a reason I do that, but it's not a good reason. Here's the two takeaways because I'm going to shift. Like this is supposedly background, and we have 30 minutes, which is perfect. And well, anyway, and I may be interrupted momentarily at any time, temporarily at any time. The two takeaways. Okay, the first thing to understand about this is it's a known this is one of the reasons we call this law or this force universal is that it involves action at a distance, meaning it happens through empty space or equally through matter. No matter is needed. This is very important. If you have a bit of the sun over here and a bit of the earth over there, they automatically pull on each other just by virtue of existing in the world. That's very important. Neither the sun nor the earth or nor the moon nor a piece of a human body or a piece of a brick, like nothing, matter doesn't have to do anything nor touch any other matter nor be in contact with anything that's touching other matter in order for matter to gravitationally pull other matter. It's a big idea. We don't need a thingy thing in between 2 points of mass to transmit or exert the gravity. And furthermore, this is why I say nor relevant. Furthermore, you could put thingy things in between two pieces of matter and they won't interfere with or block the gravity. Like the sun, the center of the sun pulls on the center of the earth, whether or not there's stuff in between the sun and the earth. Or, and put another way, the coffee mug on my desk is being pulled to the center of the earth even though there's a desk in between the coffee mug and the center of the earth. The desk that's in between the coffee mug and the center of the earth doesn't block the gravity. It doesn't stop the gravity. It just introduces another force that counteracts the gravity. Gravity's pulling the coffee mug down, mg, while the normal force of the desk is pushing the coffee mug up so the coffee mug doesn't fall. But it's not because the desk removed gravity. You see what I'm saying? The gravity is there, and this is a big idea. Again, the gravity, and I'm not saying, by the way, that this is obvious that this should be true. And I'm not even pretending to claim why this is true or even that I know. I'm just saying, apparently, it is true that if you exist, you automatically pull on anything and everything else that exists without needing for there to be any thingy thing, any material medium in between you and everything else. That's why it's part of this class. Okay, it's unthingy. It's an immaterial phenomenon in that respect. We call it action at a distance. That's takeaway number one. Like, why am I like reminding us of gravity or talking about gravity in physics 204? That's reason number one. And then, or takeaway number two, or reason number two is that the math is an invert, what we call an inverse R squared proportionality. That inverse R squared, yeah. Like like conceptually, this is action at a distance. The action just happens over any distance, regardless of what intervenes in that distance. But how does this action, this force, relate to or depend on distance? It depends on the distance between two objects by virtue of inverse r squared. You square the distance and you divide by that. So the bigger the distance between two objects squared, the smaller the force between them. Okay, that's the two takeaways of gravity. Now I'm going to use those two takeaways to build a different, newer idea. I'm going to pause for a second. I know. But are we? And the one plugin that I did here, like, which was just a plugin, right? I just plugged in simple, right? Is literally, I'm going to tell you again, the level at which you really need to sort of think today in lab is that level. Like, you're going to take a very similar equation to this and you're just going to plug in numbers like that and you're going to be given the numbers and you're going to do it like 5 times and you're going to draw pictures and stuff and that's it. Okay. So again, I'm not trying to like minimize it or anything, but you don't have to get overly so could you raise your electronic hands or anything if you're following what I'm saying to sort of this level of plug and try? Do you kind of follow what I'm saying? Thank you, July. That was fast. Thank you, Josh. That was fast. Thank you, Luke. That was fast. Thank you, Dechen. That was fast. Awesome. Jaden, I see you too. Awesome. And do I see? Great, great. That's totally, yeah. And Lou, I saw Lou. Great. All right. Awesome. So, all right, wait, I'm just switching so what am I doing with that? It's not going to get any, I don't know why it's not going to get harder. It's just now we're going to get like, it's going to get like cross applied, something else. Okay. It turns out about a century later, a century and a quarter later, we learned from this French physicist, mathematician, scientist named Auguste de Coulomb. He said this idea that any point of mass automatically pulls on any other point of mass, it also applies to this fundamental aspect of the universe known as charge. The charge that you learn about in chemistry and high school, etc. The charge that seems to be packaged in protons and electrons. Just like kilograms exist in the world for whatever reason, as an inherent property of matter, of thingy things, charge exists in the world as a fundamental characteristic of matter, of material, of the tiny building blocks of material, of thingy things. And it's measured in a unit called ultimately coulombs. So apparently, sorry, there's something in the chat. Oh no, sorry. I think that's from before. Yes. Uh, uh, so apparently, if you have a bit of charge over here and a bit of charge over there, the charge separated by some displacement r vector, the charge over here will exert a force on the charge over there in a manner that is remarkably conceptually and mathematically similar to the manner in which points of mass attract one another. Both phenomena seem to permeate the universe automatically and at the same time. So oops, sorry. Sorry. Okay, one thing. Okay, so I'm saying, I'm going to give more details in just a second. I'm saying apparently there's a force between every point charge that acts in the same universal and mathematical way as the force that acts between every bit of point mass. I'm adding the little letter E now to make it clear that what I'm talking about now is the what's known as the Coulomb force, or the electrostatic force that exists among all protons and electrons. And I'll go back in retrospect just to make this clear. So everything I was talking about before was gravity. So to make it super explicit, I probably should have, added a little G or something everywhere to make it clear that was gravity. Now I'm talking about electricity. Okay. Where else did I put? So there's a little G there. Usually the two don't come up in the same context, so it's usually clear which one people are talking about. But okay, so I'm saying this is going to be remarkably similar. Okay, it's got the same format and the same universal quality. That's why I taught the gravity first, or asserted the gravity first. So chart, it's just that it's easier for most people to, well, first of all, gravity was discovered first as a phenomenon, and then electrostatics were discovered or worked out as a phenomenon. But also, it's easier. I mean, that's not a coincidence, because it's easier for most of us to picture and relate to macroscopic masses than it is microscopic charges. But what we're saying from now on is anything that I ever say or you do in the lab today about charges, if you have a trouble picturing it, what we're talking about, just instead of a proton and electron in your mind, substitute like the sun and the earth or something like that, if that helps. But I have to adjust some of the numerical details to this new law. Um, okay. First of all, the constant is no longer capital G. It's a new constant now called K, which is super annoying because we already have two Ks in this class. They're already different and confusing. I I apologize. There is an adjustment that would be made to make this a little bit more clear, but for the moment, put a lowercase e under this K so that you know it's not the other two Ks of the class. It's not the K of spring constant and it's not the angular wave number K. It's K sub E. So what does this equal? This does not equal 6.67 times 10 to the negative 11 newtons times meter squared divided by Coulomb squared. Um, it does need, it's a different number. It's a much bigger number. Yes, it needs to cancel out the units to make the answer of the force wind up in newtons. But in order to do that, it's got to cancel out different units. Masses are, well, so here's the number. The number is approximately 8.99 times 10 to the ninth, positive ninth. This is a huge number now. Okay. Newtons times meters squared over Coulomb squared. See, it's not the speed of light or something like that. It's C stands for coulombs. Coulombs is the unit in which charge is measured. Like, so this is as opposed to kilograms, which mass is measured in, right? So let me explain a Coulomb now, or let me give you perspective on a Coulomb. One Coulomb of charge is, in fact, a huge amount of charge. Um, Sort of by historical accident. It's not as small as you might think. How small is it, or how large is it? Well, this what charge comes in is these packets known as protons and electrons. You know from chemistry, one proton has positive charge, one electron has the same amount of charge but negative, right? So that amount of charge is measured in coulombs. Okay, I'm gonna do it on the next page, just to be clear. Okay, so for perspective, and you don't have to memorize any of this. This is just to give you a sense of the numbers and perspective and all that. One proton contains approximately one, I mean, and I say approximate meaning that I'm chopping off digits, not that I'm guessing or that it doesn't change from proton to proton or anything like that. It's an exact number. It's just that the digits go on forever. So we're chopping them off, if that makes sense. Um, so the charge of one proton is positive 1.60 times 10 to the negative 19th coulombs. The charge of one electron is negative 1.60 times 10 to the negative 19th coulombs. In other words, I mean, so that's a very small number, right? I.e., 1 coulomb, let me say this better, i.e., a one, if from now on I say a 1 coulomb point charge, what that means it means a certain enormous number of protons jammed all together into a tiny, nearly infinitesimal amount of volume of space. A point charge means an amount of charge in a tiny volume. A 1 coulomb point charge means a certain number of protons jammed together into that volume. Well, each proton only has 1.60 times 10 to the negative 19th coulombs. So it means approximately, I always get this wrong, billion, trillion, quadrillion, quintillion, right? So approximately 16 quintillion protons jammed together into a Euclidean dot. If you see what I'm right, just so you understand what I'm. If we so like in the lab today, they're going to give you in the board meeting of the lab, they're going to give you a problem about of a 50 coulomb point source over here and a 3 coulomb test point over here. When we say 50 coulombs, we mean 50 times 16 quintillion protons all jammed together in a tiny space. Now that's a lot. That is, sorry, I'm just okay. That is real. I mean, that's a huge number, but protons are very small. So it's a very big number. In the lab, to be realistic, we would normally play with like millicoulombs, not coulombs. A coulomb is pretty darn large, but that's what we're talking about here. Um, we're almost done, and we're almost done. always, and this is one thing I always get wrong. Hold on a second. I always, sorry. Da, 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 da. Sorry, sorry. Someone's there. One second. Oh, I'm looking at the time also. I think someone's here. One second. I know we're almost. Oh, okay. That's it. Um, So, okay, to back up for a second, we've got 6 minutes, and we're again, thank you very much. Like you're right on track. If you're following what I'm saying, you're good to go for this afternoon's lab. Um, this afternoon's board meeting. I am trying to say, if you have any electron sitting over here, oh, sorry, I just remember one. Okay, if you have any electron sitting over here, yeah, if you have an electron sitting over here, and you have another electron sitting over here, I'm saying each of those electrons has mass and also has charge. So automatically, by virtue of their mass, the electrons will pull on each other by virtue of gravity. That's like half of today's lecture, the first half of today's lecture. But by virtue of their charge, they're automatically going to push on each other through electricity. If it's literally an electron over, both are going to happen at the same time. Like mass does this phenomenon, charge does this action at a distance phenomenon. So electrons, for example, will do both on each other at the same time. Will one effect win out over the other? Yes. If you look at all the numbers, if you plug in all the numbers, and I'm not asking you to do that right now, and you keep the distances the same, the mere constant in the electrostatic equation, 8.99 times 10 to the positive 9, is far larger than the constant in the gravity equation, 6.67 times 10 to the negative 11. So all other factors being equal, all other factors meaning distance, really, the repulsion of one electron on another outweighs, so the electrostatic repulsion of one electron on another will outweigh the gravitational attraction by approximately 40 orders of magnitude, not 40 times, 40 orders of magnitude, 10 to the 40th. If you just plug in the masses of electrons and the charges of electrons and then divide by some given distance squared and multiply by you'll see that the electrostatic force is like 10 to the 40th greater than the gravitational force. So why does gravity ever even matter at all? Or how are these both coexisting in the universe? We've got 3 more minutes. Well, what you know from chemistry is charges come in 2 varieties. Well, we already mentioned, like there's protons and there's electrons, right? So plus times plus yields plus. If you plug into the equation, if you plug in the charge amounts with positive or negative signs, minus times minus also always equals plus. But plus times minus and minus times plus always equals minus. So what? So remember what we said with the unit vector formulation of gravity. It works perfectly. Negative will always be attraction, like we said before, and positive will always be repulsion. It works out perfectly because if the signs are opposite, we're going to get attraction. And if the signs are the same, we're going to get repulsion. Like, so the convention still applies that negative from now on in these universal forces always means a pull. And positive always means a push. And you'll get a pull, either if it's gravity or if it's electricity, you'll get a pull if the two charge signs are opposite. There's 2 more minutes. There's one last thing I have to say. I said the universal Coulomb constant, the electrostatic constant, is this big number, 8.99 times 10 to the net. That's true. But you'll see in the sheet that's given today, first of all, it's inconvenient to have another K in our life, but also for other reasons that we're going to get to, it becomes more convenient to write this as 1 over the number 4 times the number pi times this other number that I'm introducing now, which is a very tiny number, and it has the inverse units of the first. This is just a convention. I mean, I'll explain this more later, but I'm saying instead of writing K as one big number, we often write it as 1 over 4 times pi times a tiny number known as epsilon naught. I'm literally just telling you that. Again, you don't have to memorize the number, but you have to be able to be comfortable with either convention. So in other words, this is the last minute. So often we write the electrostatic force as 1 over 4 pi epsilon naught Q1 Q2 all over R squared R hat. This is a more common, ultimately, you'll see why it looks clunky right now, way of writing KE. And that's it. That's okay. That's all you need to know for today. You've been very patient. Again, I congratulate you. I'll be more warm about it in a week or whatever. Thank you for putting up with another electronic slog. I hope you get some rest and relaxation somehow, and stay dry. And okay, and have a great day. I'm going to teach the other class now. I mean, if you have a quick question, feel free, but I'm going to teach. Okay, bye. Thank you. Have a good day. Thank you, Jaden. Okay, I'm stopping the recording. That much I am doing.